Okay, let's get started. I think it's time to get started. So yeah, so this is not the FANG talk. This is a talk on the microservice architecture. And basically what I'm going to talk about for the next hour, roughly, is really the essential characteristics of the microservice architecture. So kind of like, you know, the motivations for it, what it actually is, and then some of the design issues that you will face and how to address them when you actually use the microservice architecture. So just out of interest, who here is using it at work? Okay, kind of grow. Roughly, I think 30%, something like that. Well, hopefully you despite using it already, you will learn something new. So a little bit about me. So, you know, over the years, I've been doing sort of a bunch of different things. Like way back in the late 80s, I was working on Lisp systems, everything from garbage collectors up to tooling. Eventually programmed in Java, wrote the book Pojos in Action, which now came out 13 years ago, like a lifetime ago. Did Cloud Foundry, PaaS on EC2, and then pretty much for the past 5-6 years, I've been focused on the microservice architecture. So traveling around the world, helping clients use the microservice architecture effectively. In fact, I just got back from a trip to Tokyo yesterday afternoon, so I'm slightly cognitively impaired. It's like my memory is not what it is right now, but given that it's actually like 6 a.m. in the morning there, I'm gradually waking up. So that's the timing worked out well.
Good morning.
Yes. So I do microservices consulting training. I have this startup building a platform to simplify the development of business applications. My book, Microservices Patterns, came out in print back in November. And you can get 40% off, you know, today only with the discount code CTWSVCC19 if you on manning.com, which you can access via that link. And then obviously I also have microservices.io, which is a collection of resources to help, specifically a pattern language and an architectural assessment tool, along with articles and example code that will help you use the microservice architecture effectively. So that's me. I just talk about one thing, pretty much. No variation on that. So, you know, this talk, it's sort of organized around 6 different visual metaphors. So sort of shapes in a loose sense of the word, because there's like an iceberg in there, which is not exactly a shape. But it kind of using these to highlight the motivations for using microservices, the definition of what the microservice architecture is, and how to address various challenges that you will face when using microservices. So the first shape I want to talk to, or first big concept, is the success triangle, which is essentially, in order to deliver software successfully, you need the right combination of process, organizational structure, and architecture. And I'll get to the details of that in a little bit. But this slide actually introduces the primary motivation for using the microservice architecture. Namely, software is eating the world, so it doesn't really matter what sort of vertical you're in. It's extremely likely that you will have to, that software will be central to how the services and products that your business, you know, offers to the marketplace, you know, it's all going to be powered by software. So you have to develop a capability in delivering software effectively, and then combine that with the fact that the marketplace is increasingly sort of dynamic, volatile, uncertain, complex, and so on. So that actually means that you actually have to deliver products and services at a much faster rate. And of course, well, if everything is based on software, that actually means that we as software developers need to deliver software much more rapidly, frequently, and reliably. You know, there's sort of numerous examples of this happening, right? Like, couple of months ago, I read an article about how in Hong Kong, though of course they've got some issues there, suddenly like 8 virtual banks were licensed. So the incumbent there was like, wow, we've got 8 new competitors just appeared all of a sudden. And then in the insurance space, like if you want to be an Uber or Lyft driver, you should have commercial insurance, right? Some company is actually offering hourly commercial insurance, which, you think about sort of traditional insurance companies with mainframe-based systems, it's like, how are they going to adapt to that? So, the world is much more dynamic, and companies need to deliver software rapidly, frequently, and reliably. And you can actually quantify that with a combination of these metrics. So there's a couple of metrics to do with velocity. So those are lead time, the time from a developer committing or checking in a change to that change being deployed into production. And you want to minimize that so the developer is getting fast feedback. And then corresponding to that, there's also this notion of deployment frequency. How often are you pushing releases changes into production? And the fact that the unit there is deploys per developer per day, hints that it's fairly often, right? It's no longer good enough to have quarterly releases or monthly releases. Today the state of the art is pushing changes multiple times into production. And ideally, each day the developer is committing a change to trunk that's automatically being tested and deployed into production. So you're seeing companies deploy at a very rapid rate. While I've been speaking, Amazon is already, they deploy every 1.5 seconds or so. There you do the math, they've got thousands of developers. Maybe not so much on Saturday, right? But in general. And then also you're doing this extremely reliably as well. I think for many of us, pushing changes into production is an extremely stressful thing, right? You want to make it as just, deployment should just be a normal, low-stress thing. And actually, if you up the deployment frequency, the failure rate actually goes down. So you've got these metrics around change failure rate. How often do deployments actually cause an outage? Well, that you want to lower that, obviously. And then if there is an outage, you need the right mechanisms in place in order to quickly recover from a failure, quickly detect it, quickly figure out the root cause, and quickly fix it. So we need to so kind of the goal really is to optimize these metrics. Then another challenge that you're actually facing is that if you are successful, your application will typically live for a very long time, right? Like today, there are Java applications that were written like 15 years ago, right? Or there's even applications written using older technologies that have been around for 20 or 30 years, possibly. And the challenge, of course, you have is that technology changes. And you really want to be able to modernize the technology stack for your application. Otherwise, you're going to be building on something that is increasingly obsolete. And I think that's a major challenge for a lot of applications, right? They're just sort of ancient legacy technologies, Cold Fusion, RPG, and so on, 4GLs and the like. So that's sort of the challenge. We've got to be able to deliver software quickly, and we want to be able to modernize our applications. And so in order to do that, you need this success triangle, which is kind of sort of slightly cute marketing thing, but it means that you actually need the right combination of process, organization, and architecture in order to be successful. Now, in terms of process, there's a strong consensus that you need a combination of sort of lean product development methodologies along with DevOps as your software delivery methodology. And actually, it turns out that DevOps means a lot of different things to a lot of different people, but it's basically a set of principles and practices for rapidly and reliably and frequently delivering software. And it's kind of a combination of agile along with continuous delivery and continuous deployment. So that's how, from a process point of view, we should be developing software. And then organizationally, there's a lot of evidence to suggest that instead of having siloed organizations and large teams, you want to sort of slice that up and restructure it into a set of small cross-functional teams, each one focused on a particular functional area of the business, and they are loosely coupled, which means that they don't have many meetings to plan their work amongst the different teams. They're all highly productive, working independently most of the time. So then that leaves the third part of this architecture. What architecture do we need in order to do DevOps, and what architecture do we need in order to have these, to enable these small teams to be autonomous and highly productive? And of course, this is a talk on microservices, so the answer there should be obvious. But I'll get there in the next section. So anyway, so that's the success triangle, the three things that you need to have in place in order to deliver software successfully. So from an architectural point of view, it actually requires your architecture to have certain quality attributes or certain ilities. And so, if you want to do DevOps, you need an architecture that is highly testable, highly deployable, and also highly maintainable as well. In particular, sort of testability and deployability are key enablers for doing DevOps, which relies on a high level of automation and so on. And then, of course, in general, you need things to be highly maintainable as well. And then to support loosely coupled teams, you actually want to sort of think in terms of Conway's law. And so a loosely coupled organizational structure requires you to have a loosely coupled modular architecture. Conway's law basically says that the architecture and the organization that created it mirror one another. And so loosely coupled teams require a loosely coupled architecture. And then in terms of what you need for long-lived applications, you also need a very modular architecture so that you can replace parts of it piecemeal. And sort of in general, you need an architecture that's highly evolvable as well. So those are sort of what we need from our architecture. Now, if you look at a sort of standard architecture, the typical thing, like pretty much everything I've built over the years until relatively recently had a monolithic architecture. So from sort of a logical perspective, it was layered and modular. But then it was basically one code base that all got packaged up as a single deployable unit. So this was Java, so it got packaged up as a WAR file. Maybe before that it was an IR file. If this was some other language, maybe it gets built into a single executable. So that's the monolithic architecture, which in itself is not an anti-pattern. It's important to remember this, right? You can have a monolithic architecture that is highly testable, highly deployable, maintainable, and somewhat modular as well. And somewhat evolvable. Though obviously, if you've got a modular architecture, you typically have to use the same language throughout, or at least the same runtime. It has to be JVM-based, for instance, even though you could have a mix of JVM languages. You can't have a monolith, at least as far as I know, where part of it is written in Java and other parts written in Golang, unless someone's done something weird and wacky. So there you are constrained in terms of how you can evolve your modular architecture, or your monolithic architecture, which over the long run will actually lead to problems. But sort of more importantly, if you have a successful application, it tends to keep growing, right? In the beginning, it's a tiny little team, right? And a tiny little application, but the developers are just writing code all day long, right? They're writing their 20 lines of tested production quality code or whatever the metric is each day. And so over time, the application is getting bigger and bigger and bigger, right? And the development team, if you're making money, will be getting bigger and bigger, so the rate of change is actually increasing as well. And you might try and split up the development team, but they're all contributing to this increasingly large monolithic code base. And then usually what happens there is modularity will break down and you end up with a sort of difficult to maintain big ball of mud, which sort of seems to be the standard architecture for most enterprise applications. And then you basically are locked into whatever technology choices you made at the start of the project. You've got this massive code base, And yeah, you can change a few parts of it, but you can't rewrite it to use a different language, or you can't switch to another application framework. And so you're pretty much stuck with the choices that you made at the start of the project. You know, I've even encountered organizations that are stuck using an older version of Spring, because to upgrade to a new version of Spring, they actually have to upgrade to a new version of Hibernate, so they tend to be stuck with some ancient version of the Spring framework, which means you can't take advantage of all of the new goodness. And that's just within, even though the Spring framework is basically backwards compatible. So that's a challenge. And if you're using some language, you know, like I think the other day I ran into people who are using Cold Fusion, right? Something for the history books. You know, it's very hard to get out of that situation without a massive rewrite that's very expensive and very risky. So basically, the picture is this, where, you know, over time, the size and complexity of the application grows, but all of the desirable sort of quality attributes of your architecture just kind of decline over time. And it just gets harder and harder to deliver software. And this is a huge risk to the business, because the ilities that you need actually are kind of going in the opposite direction, right? So there's this increasingly large gap between the ilities that you have and the ilities that you need. And that's where, you know, that presents a risk to the business of being disrupted by some fast-moving competitor. And in fact, you know, I don't know if this will ever work out, but the insurance company that was offering hourly commercial insurance to Uber drivers was saying the legacy insurance companies will never be able to compete with us because of their archaic systems. So I don't know if that's just sort of bragging and they'd get beaten eventually. So anyway, so that's the problem that you typically run into if you have a monolithic architecture. So a few years ago, 9 years ago now, I was reading this book, The Art of Scalability, which I think that coincidentally was written by people who were at eBay and PayPal, you know, which 10 years ago, super awesome, cool thought leader in e-commerce, right? And one of the interesting things in that book is they had the scale cube, which is a three-dimensional model of scalability. So in other words, there are three different ways of scaling your application. You have x-axis scaling or horizontal duplication, which is where you're running multiple copies of your monolith behind a load balancer. That's everyday scaling. Then there's z-axis scaling, where you're running multiple copies of your monolith behind a load balancer, which is slightly different. It uses an attribute of the request to route that request to the appropriate destination. So in other words, some customers get routed like over there to some pod over there, another set of customers get routed to a different location. And then at the database level, that would be called sharding, where the primary key of the row determines which server that row resides on. But both X and Z axis scaling are ways of scaling the monolith. But there's also Y-axis scaling or functional decomposition, which is quite different. The first two are focused on sort of dealing with transaction and scaling to deal with transaction volumes and data volumes and availability. Y-axis scaling is about primarily tackling complexity, system complexity, by applying functional decomposition and breaking what would otherwise be a monolith up into a set of services. And so that's essentially my kind of, to me, the origins of the microservice architecture. Don't build some big thing that's like difficult to maintain, break it up into a set of smaller pieces. So this then leads to this definition of the microservice architecture. So it's a way of structuring an application as a set of services, and each service is basically a mini application, where each service is highly maintainable and testable, given that that's the goal. It's loosely coupled, which enables the teams that work on the service to be loosely coupled. It's independently deployable. It tends to be organized around a business function. So, you know, like account management, customer management, and so on. And then the last part, which is extremely important, is it's owned by a small team. So going back to the original notion of having an organizational structure made up of loosely coupled small teams, right? You need services that are small enough that they can be owned by a small team. Now, interestingly, you can see that I struck through the phrase micro. I really don't like that because that implies that a service should be tiny, like 100 lines of code, 1,000 lines of code, 2 weeks worth of work. Those are all kind of stupid metrics that are best ignored, right? The only requirements really around size come from the fact that it should be highly testable and maintainable, right? Like the code should fit in a developer's head. So if the code base is getting too large to understand, that's a sign that your service is getting too big. And then, of course, it should be owned by a relatively small team. 6, 8, 10 people, not really any larger than that. And you should really just start off with one service per team. I mean, there's a lot of focus today on like these very fine-grained architectures, mostly because companies that sort of give talks at conferences go, hey, we're Uber, we've got 2,000 services, aren't we cool? So on and so forth. I mean, they're kind of cool in a way, but they end up, it's almost like the pattern is a service per developer, which I think arguably is too fine-grained and overly complex. Given that the goal really is team autonomy, you can achieve that with one service per team unless that is demonstrably a problem. Like maybe the service actually has got too large so that it takes too long for the deployment pipeline to run. And so there's real value in splitting it up into smaller services that can be changed, tested, and deployed much faster. But the starting point is one service per team. So then if I go back to the food application, the food-to-go application, which is the example from my book, it looks like this. You've got a bunch of services, each one performing a particular business function. Each one of them has its own database, which is important for loose coupling, and I'm going to talk about that more later. They might actually communicate via a message broker for reasons I'll get into. You can functionally decompose the front end as well, like different server-side web applications responsible for different parts of the user interface. If you're exposing an API gateway to the outside of an API to the outside world, that's typically done with an API gateway. So in this example, there's JavaScript running in the browser and a mobile application making REST calls to the API gateway that's routing to the relevant services. Gosh, this is a bit more complicated than the previous one, right? Which actually hints at one of the drawbacks of this architecture, lots of moving parts. And I'll talk about that a little bit in a minute. But that's the idea. So it's sort of you break it apart into a bunch of services. And it's important to remember that each one of these boxes is a design time concept, which at runtime will actually consist of multiple instances. So each one of them is basically like a set of load-balanced processes, or Docker containers if you want to be, if you're using Docker. So there's a bunch of benefits to this, right? Like the fact that each service is small, it's not necessarily tiny, but it's small makes it easier to test, easier and faster to test, which improves testability. It's also easy, by definition, it's independently deployable. So the team that owns it can work on it, build it, test it, deploy it independently of any of the other services. It's also much more maintainable, of course. It's also a very modular architecture because you've got these remote APIs for each service which cannot be bypassed, so it preserves modularity. And then also it's highly evolvable as well. You can evolve the technology stack for each service independently. So you might have a bunch of Java services and decide, well, I want to use Golang because Google uses it and therefore it's cool. And if you have success with Golang, that's great. But if you decide that it's too low level, it's not a disaster. You've learned something. You've learned a valuable lesson, and later on you can replace that with a more, higher level language. And that's a really key attribute. You do not have to upgrade the technology stack for your entire application simultaneously. So it becomes feasible to incrementally migrate to a newer technology. But relating this back to the success triangle, right? This architecture gives you the testability and deployability that you need in order to do DevOps. It gives you the modularity to support these small autonomous teams. And then it also gives you the modularity, the evolvability, and the maintainability to enable you to have these long-lived applications that you can incrementally modernize to newer technologies. But of course, there are some downsides. You got a taste of that from the previous architecture diagram. Namely, there's all of this complexity, many more moving parts. You are now building a distributed system, so you have all of the development challenges of doing that. Namely, you have to deal with inter-process communication. You have to deal with the fact that when service A invokes service B might not actually be running at that point in time, or it might be exhibiting extremely high latency. So there's a bunch of challenges around that. Also, the fact that each service has its own database, it creates some really interesting challenges around distributed data management. And that's like a whole other complex topic. And in particular, you have to give up using ACID transactions between services and use eventually consistent sagas as well. Testing is simultaneously easier because each service is easier to test, but then there are challenges around testing the interaction between the services. You have to use what's known as consumer-driven contract testing in order to test each service independently while being confident that they actually can collaborate. And then there are challenges around deployment, but today there are sort of modern deployment platforms like Kubernetes or AWS Fargate or Lambda or so on that automate a large part of this. And then a big challenge is actually just figuring out what your service boundaries are and making sure that you have services that are in fact loosely coupled. And actually resisting the temptation to have a too fine-grained architecture is another challenge. And then also, breaking apart your monolithic application into a set of services is actually a challenge as well. Like, it's a slow, painful, and quite often a multi-year process to re-architect your system into a set of services. But companies have done that successfully. Okay, so that's the scale cube, which kind of like is the definition of the microservice architecture. Kind of want to dive down into the structure of an individual service. Now, what's interesting is we like to think in terms of a three-tier architecture for applications or services, right? Where we've got a presentation layer, which invokes the business logic, which invokes the persistence layer. What's fascinating about this is it often doesn't reflect reality. In particular, the business logic usually does not depend on the persistence layer. It's actually the other way around, which doesn't, so this layered architecture doesn't look quite right. And also the fact that there's usually more than one sort of so-called presentation layer and possibly more than one persistence layer. So for that reason, I don't like to use this sort of three-tier, this layered architecture to describe the architecture of my services. And I find that a much better way of viewing a service is using the hexagonal architecture. And I think there was a talk on that earlier today, right? Which also goes by the name of ports and adapter architecture. So in this, not only you have like a visually attractive hexagon, well, a couple of hexagons, right? Where the business logic is actually the core of the application. The business logic has a number of ports, which are basically interfaces there are two types of ports. There are inbound interfaces, which enable the outside to invoke the business logic. And then there are also outbound ports, which enable the business logic to invoke things on the outside of it. And then, around the edge of the service, you have adapters, which handle external requests. So you might have an inbound adapter, like an order controller, which handles an HTTP request, and it calls some inbound port on the business logic. And then you might have an outbound port, like a database adapter or database access object, which actually implements the outbound port interface and does the actual database access operations. You might have other adapters as well, like ones that subscribe to message brokers or make outbound calls using REST or some other protocols. So it's a kind of a more accurate way of thinking about the architecture of the service. Now, in terms of actual details, right, you know, a service, kind of the reason for a service to exist is to expose an API to its clients. You know, that's its whole reason for existing. Now, the API of a service consists of two parts. The first part are the operations that can be invoked. And there are two types of operations. There are commands which change data. So if this was the order service, it would be like create order, revise order, cancel order. And then there are queries, which are operations that retrieve data without changing it, like find order history, etc. And then there's two different ways of invoking those operations. And we always think about using REST or gRPC. So those are synchronous protocols. And there are obviously other protocols synchronous protocols you could use as well. But then often in a microservice architecture, for reasons I'll get into later, you might invoke these commands or queries asynchronously by sending a message to a service via a message broker. So that's one part of the API, the operations. The other part of the API are the events that a service can emit. It's quite useful for a service to emit events when something of interest, which is normally the creation or the update of some business object. So in domain-driven design terms, these are typically, service will emit domain events when one of its aggregates is updated, changes. So in other words, it's publishing these events to a message broker, and then interested consumers can subscribe to them. So that's that's the API of a service. The service can also invoke operations implemented by other services, and it can also subscribe to events that are emitted by other services as well. So that's kind of the black box view of a service from a development perspective. There's this operational view of a service as well, which I'll talk about in a minute. So for instance, the order service in my book's example application implements a create order operation, which is really a post to /orders. It emits events like order created, and then it asynchronously invokes other services like the consumer service. And for reasons I don't have time to go into, it's subscribing to events emitted by the restaurant service. So when a new restaurant is created, the order service is told about it so that it can start accepting orders for that restaurant. There's a bunch of details there, but that's sort of to give you a flavor. Then there's also the the operational aspects of a service. It will typically implement some externalized configuration mechanism. So for instance, you will typically build a service once and then run it in different environments. Testing, staging, production. You cannot hardwire the database credentials into the service, for instance. You want to pass those in at runtime, and that's the job of the externalized configuration mechanism. That might just be as simple as reading environment variables, or maybe more complex. It might reach out to a configuration server and pull in those values. The service also has to log, right? That's pretty straightforward. Yeah, in Java, multiple logging frameworks, not a problem. It also typically has to implement a health check API that the runtime infrastructure can periodically ping to verify that the service instance is healthy. And that was typically like a /health REST endpoint or a /HC. A 200 indicates healthy. Anything else, including not responding, within a timeout period indicates that the service instance is unhealthy, and the runtime system will typically kill it off and restart it if there's so many failed health checks in a row. A service also needs to gather metrics and export them. So these are like counters, for instance, of like for the order service, how many orders were created, how many were rejected, how many were accepted. So those are sort of business level metrics in addition to all of the runtime metrics like heap utilization and stuff like that. Those get reported into a metrics database where they are aggregated and where they can be visualized, and you can set up alerts to notify operations of abnormal behavior. And then a service typically has to participate in a distributed tracing mechanism. So when a request comes in and bounces amongst multiple services, you can actually visualize, where you can actually track that and visualize it and so on. So it's sort of like you need all of this in place in order to have a production-ready service. So that's sort of the operational aspects of the service. So I want to talk next a little bit about some design issues that you will face. Now, sort of one of the goals here is you want these services to be loosely coupled, right? Services often have to collaborate in some way, right? They're not like these sort of little islands where they never communicate with one another. I mean, that's the ideal state of affairs, but usually there is some requirement for some degree of collaboration between services. So some form of coupling is inevitable, but you want to make sure that it's actually loose coupling as opposed to tight coupling. There's actually two different types of coupling. So there's runtime coupling, and so two services are tightly coupled from a runtime perspective. If one service, like in this example, the order service, cannot respond to a request until some other service has responded to it. And I'm going to talk about that later, but that's particularly problematic from an availability point of view. If you have a whole chain of synchronous communication between services, essentially each one of those services becomes a single point of failure. So you've sort of got a very brittle architecture. But then the other type of coupling, which can have a dramatic impact on team productivity, is design time coupling. And so that's where once, like in this example, the order service depends upon the API of the customer service, and if that API is changing a lot and enforcing changes to the order service, then they're effectively tightly coupled from a design time perspective. And that's particularly problematic, because remember, the goal is for these teams to work independently most of the time. But if, the order service team is constantly having to deal with changes to the customer service API, which will probably involve meetings with the customer service team, right? In order to plan the changes and discuss them and review them and so on and so forth, that's really going to slow down development, right? Because you got to plan meetings and you got to find a meeting room, which, as far as I can tell, globally, there's never enough meeting rooms. And there's actually, there is a statistic that says decisions that go outside of a team take 10 times longer than decisions within the team. So any kind of API changes which require coordination is quite problematic. So you want to make sure that your services have these well-defined static APIs, and you want to avoid, or stable APIs, and you want to avoid shared libraries as well. So I like to think of services as really looking like icebergs, where they've got a small, relatively small, stable API that's encapsulating and hiding a lot of implementation details, which relative to the size of the API are quite large, because that means that the team that owns that service can be busily working away and improving that service without regularly impacting the API. And when they do change the API, they should do it in a backwards compatible way. And I think of companies like Stripe, right, where that presumably there's a tremendous amount of complexity there, but the actual API itself, which is like charge this credit card, is really, really simple. Or Twilio, right, the communications company, where like one of the operations is send this SMS to this phone number. Incredibly simple API, which presumably hides a massive amount of complexity. So you want to kind of think of your services in those terms. And in particular, you want to avoid kind of like these CRUD services, which are basically all API and no implementation, right? Where they're basically just wrapping a database, and there's sort of a one-to-one correspondence between the database schema and the API. There's basically no kind of encapsulation there. There are even tools, right, that will rapidly generate services like this from your database. So they're basically anti-pattern generating services, and will just lead to grief. Obviously services have a database, but they should have they should have a significant amount of business logic in there, and look more like this than like this. And then this also means that you should avoid shared database tables as well, because sharing of tables is both design time coupling, right? Like schema changes have to be coordinated amongst all of the teams whose services access that table. So that slows things down and actually ultimately can prevent you from changing the schema. It just gets too difficult to coordinate. And then it also implies runtime coupling as well. One service can claim a lock on a table that prevents another service from operating. So that's undesirable. So tables rather should be considered private to a service and only indirectly accessible via that service's API. And that's a kind of a big cultural shift, I think, for a lot of enterprise developers who think in terms of database tables, right? In this world, it's APIs. You do not have tables. Okay, so moving on. So that's sort of another triangular shape. So the next shape I want to talk about is the cylinder, which is sort of the metaphor for using asynchronous messaging. So I want to talk a bit more about using synchronous communication between services. So something like REST or gRPC, or I suppose there's Thrift and other things like that, right? So imagine you've got an architecture that looks like this, where the order service, gets a request to create an order. In order to do that, it needs to reserve credits in the customer service. So it makes a put request to the customer service, and it's sitting there waiting for a response to come back, and one does, and then it can finally return a response to its client, right? So it's sort of like, well, here we might have taken some modules that existed in our monolith and replaced method calls with REST, and it all seems kind of simple, right? But the problem you have is that this can impact availability. So the availability of in order for the create order operation to work, the order service must be up and the customer service must be up as well, right? And so the availability of that operation is the product of the availability of the two services. And in general, the availability of an operation is the availability of one service to the power n, right? And so, like one client I visited recently, like a key operation involved 9 services, right? So in theory, availability is is the availability of one service, the power n, and suddenly, high availability becomes not so much availability, right? And yeah, there's things that you can sort of do to make sure that services are available, cluster them, load balance them, and so on, but it is problematic. And sort of like, you're kind of, it's like an anti-pattern where you're considering distributed programming as free and you're incurring latency costs plus you're risking lower availability. So for that reason, it's much better for services to use asynchronous messaging. A good model for that comes from the book, which is probably difficult to read, Enterprise Integration Patterns by Gregor Holpe, which is kind of like the Bible for messaging systems. The model is, right, sender sends a message which consists of a header and a payload to a message channel, which is an abstraction over whatever your messaging system provides, and then the messages are read by a recipient. And it's a nice abstract model that's independent of technology. And then ultimately can get mapped down to whatever messaging capabilities your broker has, right? Whether that's Kafka topics or Apache or JMS queues or topics. And there's actually two types of channels, point-to-point channels where a message is delivered to one receiver, and publish-subscribe channels where they're delivered to all receivers. And different scenarios require different channel types. So you can so that ends up being a good mechanism to use in a microservice architecture. So, and there's a couple of different ways that you could use it to implement the create order operation. So one of them is where the post actually returns immediately. So in other words, the order service kind of creates an order, and so it generates an order ID and then returns it to the client, but says, essentially I'm saying, I've received the order and I'm in the process of creating it. Please check back later to see what the status of that order is. And then in the meantime, the order service and the customer service collaborate by exchanging messages. And in this example, they're exchanging events. And this is known as a choreography-based saga. So the order service publishes an order created event, which triggers an event handler in the customer service, which then tries to reserve credit, publishes an event, which then gets consumed by the order service, which can then either approve or reject that order, depending on the outcome of that credit reservation. So all of the interaction between the services is actually handled sort of, quote, offline in the background. And the value of this is that it improves the availability of the create order endpoint, right? Provided the order service is up, doesn't matter what's happening with the customer service or the inventory service or the 45 other services that need to participate in the creation of the order, right? Eventually, the order will be approved or rejected. So it's a more available architecture. But obviously, it's more complex, right? You've got this complex collaboration mechanism. Plus, the response to the post cannot contain the outcome of can't tell the client whether the order has been approved or not. It has to check back later. So you're pushing more work onto the client. Another option is actually to use events to replicate data. So the idea here is well, the customer service no longer keeps track of available credit. That's actually now maintained in the order service. So the credit limit, which is maintained by the customer service, is actually replicated to the order service. So the order service knows what the credit limit is, and then it can calculate the available credit itself. And that's done using events, and this is the CQRS pattern. So it means that the order service has all of the data that it needs in its database to decide whether to approve or reject the order. So it's sort of interacting asynchronously in a different way with the customer service. So you get better availability, plus it does mean that the response can contain the sort of the outcome of doing the validation. The downside is that you've got the cost and complexity of doing all of this replication. Interestingly, I think the first time I gave this talk was actually in Australia, and I just said, hey, you've only got 20 million people, right? That's not a very big, that's a laptop scale database, right? And then I gave the talk in Singapore, and I think there's only 5 million people there, right? Though, you know, obviously if you're Amazon.com or Facebook, where you've got like gazillion customers, then replication at that point is non-trivial. But depending on your business, it might not be. So it's sort of like, so you want to have services communicate asynchronously, and there's a couple of patterns for that, sagas and CQRS. So that's messaging. Last thing I want to talk about is testing. So just a quick poll. Who works at a company where you do automated testing well? Yeah. Oh, how about where there's no automated testing? All right. So I have a slide to show that you're not alone. So it turns out that, yeah, automated testing is a real interesting issue in a lot of companies. It was like a year ago, I actually met Kent Beck. And I said to, you know, and it's like JUnit, right? It's 19 years old. And it's like, when do you think this automated testing thing's going to catch on, Ken? But the interesting thing is, right, is that microservices is all about enabling DevOps. DevOps, you know, basically mandates automated testing. And also the inherent complexity of the microservice architecture actually requires automated testing as well. So trying to do microservices without automated testing is sort of self-defeating and risky. And it's actually this anti-pattern I've observed at a lot of companies. And this was a really interesting survey. So it's from the state of testing, and it was done, 2018. And basically, 2% of companies are fully automated, 26% of companies are mostly automated, which means that, like, you know, 72% of companies are still relying heavily on manual testing. Wow. Which is like, oh my God. Yeah, and then apparently there's 8% of companies that are like fully manual, right? What's? Yeah, I'll get to, actually I have a slide on that later. And it's fascinating because there's also a poll that says like 90% of companies want to do DevOps and Agile, I think. So there's like a total disconnect here. So testing is really important. A really useful concept is this testing pyramid. And there's a little bit of debate about whether it's really pyramid shaped or not. But basically the idea is that tests at the bottom are reliable, fast, and cheap, whereas as you move up, tests get increasingly brittle, like they just fail randomly, and they're also slower and much more expensive to write. And then, so the pyramid is comprised of layers, right? And there's different types of tests. So at the bottom, you've got unit tests, where you're testing individual classes. Above that, you've got integration tests, where you're testing the adapters of your services. Then you have component testing, where you're testing an entire service. And then there's end-to-end testing, where you're testing essentially the entire application, an entire set of services. And interestingly, I would make an argument for basically trying to avoid that as much as possible, which presents a whole bunch of challenges, especially if your tests are written in terms of user scenarios which span a lot of services. And I'll talk about that in a minute. But that's the idea, and you really want to push the testing as far down the pyramid as possible. So in particular, if you've got like a complex algorithm for calculating the repayment schedule for a loan, please test it down here with simple JUnit tests rather than like testing it through the UI up at this level, because it's much faster and much more reliable. the path from developer laptop to production is this automated deployment pipeline that runs a series of tests of increasing kind of complexity, and it could include performance tests, and though those are often best done in production, along with maybe some other kind of non-functional tests, and perhaps ideally the last step is an automatic deployment into your production environment. Or maybe you push a button to trigger the final step, right?
One of the interesting cases is ratio upgrade your service is not completed in the deployment at the requested service, for example, 50/50.
Oh, yeah. Yeah, I mentioned that in a bit. And so the model you have is that each service should have its own deployment pipeline. So each team's working away on their service, testing their respective bit, their service, and then gets pushed into production. There might be a later phase that does some end-to-end testing, and I'll talk about it in a minute. I'm running out of time. So the one thing I want to talk about is this consumer-driven contract testing. And that's the goal of this, is to verify that a service and its clients can communicate. In other words, they agree on the API, but you actually test each one in isolation. So you avoid doing an end-to-end test to make sure that your services can communicate. And the example I use is this, where you've got an API gateway that's making a GET request to the order service. The classes that are involved are the order service proxy and the order controller, right? And you actually you test that they can communicate by testing those individual classes in isolation. And you do that using contracts. There's a few different contract testing frameworks. The one I'm using here is Spring Cloud Contract. And with that, the interaction between services is described by a set of contracts, and each contract is an example HTTP request response pair. So it's like API definition by example. So whereas Swagger is like an abstract definition, right? This, or OpenAPI, I should say, this is a set of concrete examples. So it's saying, well, when I send this request in, this is the response that I expect back. And it's actually, these are written by the client team, which in this case is the API gateway team. The first use of them is to test the client code, the order service proxy. These contracts are used to configure a simulation or mock of the order service API. And I'm doing that here with this wire mock. That's an open source sort of API simulation tool. So basically, it's configured with these contracts. And so in other words, when it sees a request matching this, it will send back the corresponding response. So the order service proxy class that we're testing is just making calls, and it doesn't know that it's communicating with a simulation. So that's great. We're testing with a mock, so we're testing in isolation. But in order to make sure that the mock is accurately simulating the service, those contracts are actually used to test the service as well. So there's a bunch of complexity here, but basically we're testing this order controller class in isolation, and the code-generated tests send in the request from the contract and verify that the response that comes back matches the response in the contract. So it's saying, if it sends this in and verifies that the response matches that. And because those contracts are actually used to test both, if the same contracts, it basically means if both parties agree, then fingers crossed, when you deploy them into production, they will work, they actually agree on what the API is. And that's kind of a key mechanism to do the testing in isolation, which is much faster than writing these end-to-end tests. I mean, there's a whole bunch of details that I glossed over, but hopefully I communicated at least the intent of it. So if you want, you can have end-to-end tests. So we could have a separate like end-to-end test environment where when a new service is built, that tests that new service version with the existing versions of all of those services. The risk that you run into is that these tests, they're brittle, right? Anytime you're testing a complex system, things will fail just for random reasons, right? Cosmic ray hits some server or something. And they also tend to be kind of slow and kind of complex to write. So what you can end up with is these can end up being a bottleneck, right? And yes, you can do things like you can parallelize them in some situations. But you really want to avoid having long-running end-to-end tests for no other reason other than, for example, if there's a bug in production, the longer these tests take to run, the longer it will take to actually get to fix that bug in production. So if this is taking 5 hours, yeah, you're going to be down for 5 hours, right? Unless you bypass it all completely, which is sort of self-defeating, right? So then the last thing I want to finish with is this idea of testing in production. And sort of the big concept, right? So you should test before production, but you should also, testing should continue in production as well. For the simple reason that, you might not be able to write completely thorough end-to-end tests. And also, no matter how much you test, you will still get bugs in production, right? That's just a given. So there's some really interesting concepts, like you separate out deployment, which is the act of getting things running in production, from release, which is the making that new code available to users. And you can test code before releasing and actually while you're releasing as well. Plus a high level of automation and error detection, so you can quickly detect an error and roll back. And so I think I'll finish with this, right? So the general idea is you can actually deploy version 2 alongside version 1 behind an intelligent traffic router. You could then test it in whatever way you see fit. You can then configure the traffic router to allow test traffic, like from internal users, to go to version 2, make sure it's working. And then you can gradually route an increasing percentage of test traffic, of actual production traffic to the new version while monitoring it carefully. Like you can monitor based on latency and also like errors, like how many 500s you get. And if you see a spike in latency or a spike in the error rate, which is indicative of a problem, you can actually quickly change the routing rules to route all traffic back to version 1 while you diagnose the problem. But you're just incrementally routing more and more traffic to version 2 while making sure that things are working until you end up with all of the traffic going to version 2 and none to version 1. And then eventually you can retire version 1. So that's sort of this whole mechanism of canary deployment. And the good news is that there's a whole concept of a service mesh, which is intelligent network routing, among other things, that make this fairly doable today. Like basically these routing rules are now just simple YAML files that you just use to configure something like Istio and so on. And there's some more general concepts around testing in production that I don't have time to go into. So I really should wrap things up here. I hate to run long, because I've already gone a little long. But anyway, so those are the key ideas. It's all about the scale, the success triangle, the scale cube, the hexagonal architecture, then loose design time and runtime coupling combined with the test pyramid. So that's my talk. Thank you for listening, and I hope that you found it useful. Thank you.